Nigafar about EEGs and action potentials. We're going to provide a brief introduction to an EEG. So, what's an EEG?
So the EEG, also known as an electroencephalogram, is a recording of the electrical activity of the brain. It results from the activity of large populations of neurons. The electrical activity arises from the cortical neurons in the brain, which generate electrical currents which spread throughout the head. These currents spread to the surface of the scalp, where they are detected by the electrodes in the form of voltage changes.
The electrical activity of the brain. The electrical activity of the brain can be better understood if we consider the mechanisms by which electrical impulses are generated in neurons. Electrical impulses are generated as a result of a neurotransmitter binding, creating an EPSP, which in turn initiates an action potential. The EPSP is the excitatory postsynaptic potential. It is due to the temporary depolarization of postsynaptic membrane due to flow of positively charged ions into the postsynaptic cell as a result of binding of neurotransmitters from presynaptic axons. An action potential is a rapid reversal in the voltage of a cell. We have a resting phase where the membrane is at equilibrium voltage of minus 70 millivolts. We then have an initial stimulus, which is as a result of an EPSP. This leads to a depolarization, which is a rising membrane potential as a result of an influx of sodium ions. After the peak, we have a repolarization, which is when the membrane potential returns towards the equilibrium voltage due to potassium ions influx. This is as a result of closing of the sodium channels that open in depolarization and the opening of new potassium channels. Throughout this whole process, we have a refractory period, which means the membrane cannot respond to stimulus.
So in these next few slides, we'll be talking about the physiological basis behind an EEG signal. So this can be further explained by considering the electrical activity of a single pyramidal cell activated by an afferent pathway. So the incoming signal at the synapse gives rise to a postsynaptic potential resulting from the positively charged ions rushing into the cell. As this current propagates down the conductive dendrite of the neuron, the size of the EPSP decreases. This leaves a relatively negative charge in the extracellular space immediately surrounding the synapse. A dipole is therefore created with separation of charge vertically orientated in the cortex. Every neuron is receiving synaptic inputs can therefore be thought of as a dipole with a specific orientation and polarity. Signals cannot be detected from single neurons, as the potentials are of very small magnitude and on the cellular scale are considerable distance from the cell-to-scalp surface. The signal detected is in fact the summation of all the dipoles created at each of the 1,000 neurons.
So, how are EEG measured? EEGs are measured using the International Federation 1020 system. This involves using 21 silver-silver electrodes placed at specific anatomical points on the head of the patient. A differential signal is amplified and displayed as a channel of EEG activity. This representation of the EEG channels is called a montage. There are four types of montages: bipolar, common reference, average reference, and Laplacian.
So now we're talking about the uses of EEG. So in clinical medicine, EEG is mainly used to help diagnose epilepsy and seizure disorders. EEGs can also be used for patients who are in a coma. In this situation, the EEG can help determine the severity of brain damage. Other uses also include dementia, head injury, vertigo, brain tumor, brain abscesses, encephalitis, and sleep disorders.
Brainwaves. These occur in humans either awake or when asleep. We have four main types of brainwaves: alpha, beta, theta, and delta. Alpha waves occur when you're in normal, quiet, resting state. Beta waves occur mainly during intense mental activity. Theta waves occur during periods of emotional stress, while delta waves occur in deep sleep and serious organic brain disease. Like I said before, these waves can also occur in sleep, and so you can see these activity in the different stages of sleep as well as REM. Now we'll talk about seizures and epilepsy.
So what is a seizure? Well, a seizure is a clinical manifestation of a sudden surge of electrical activity in the brain, arising from abnormal and excessive excitation and synchronization of a population of cortical neurons. Epilepsy, in contrast, is a chronic neurological dysfunction characterized by recurrent seizures. So seizure types are organized depending upon the location of the seizure within the brain. In partial, the seizure activity originates in one part of the brain, whereas in generalized seizures, the seizure activity involves entire brain regions. So how can an EEG detect abnormal brain activity? Well, to start off with, this is how a normal EEG trace looks like. The frequency of waveforms depend upon the state of activity of the brain. In contrast, this is how an abnormal brain EEG trace looks like. Different abnormalities within the brain show different characteristic changes. For example, in epilepsy, characteristic sharp waves, spike waves, and polyspike waves are seen. These may be either focal, lateralized, or generalized, indicating the origin of the abnormality. Further clues to the brain status can also be seen by analyzing the background EEG activity. In abnormal EEGs, they may be slowing of the waves not consistent with behavioral state of the person. Significant asymmetry is also suggestive of abnormal brain activity. This is an example of a left temporal lobe sharp wave in an epileptic patient. This slide shows an EEG trace of a patient with an absence seizure. These are characterized by an EEG signal containing generalized spike and slow wave discharges. So lastly, this is a recording of a complex partial seizure. These seizures are caused by abnormal electrical activity in a specific part of the brain. In this EEG trace, we can see the abnormality localized to the temporal part of the brain.
We've been talking to you for some time now about the EEG, so this is our summary. 1. The EEG is a recording of the electrical activity of the brain. 2. Electrical signal detected represents the summed extracellular electric field potentials generated by EPSP and IPSP on dendrites and neuronal cell bodies of pyramidal neurons. Electrical signal is measured using the International Federation 1020 system. 4. The EEG is used to monitor brain activity and to detect and diagnose seizures and to aid understanding of epileptic episodes. 5. Epilepsy is a chronic neurological dysfunction characterized by recurrent seizures. And 6. There are various types of epilepsy grouped according to origin and clinical manifestations. I hope you enjoyed that presentation. Thank you.